As you see, this is about direct write technologies. This is a very specific group of processes under additive manufacturing technologies. We use these technologies especially to print very small, highly detailed products, and it's quite difficult to find commercial products utilizing these technologies. Mostly research actually is done on these technologies. So in terms of, in broad meaning, actually direct write means any kind of technology which can generate some objects on 2D or 3D structures. And the thing is that the surfaces should be as flat as possible, or you may have obviously conformal surface that is a 3D object. And the thing is that with the direct write, you start with an, seeing that if it's an, okay, let me turn this one on. So, okay, seeing that this is a kind of a 3D surface, we have conformal surface. And with the help of these direct write technologies, we try to embed some, let's say, kind of special objects, sensors even, or some other type of actuators, maybe difficult products, are embedded onto the surface of 2D or 3D conformal regions. And in the additive manufacturing community, we will be considering the direct write technologies as the technologies which are capable of actually building products with dimensions of 5mm or less than that. So these technologies are focusing on smaller products, and their feature resolutions are quite high, as you see here. It's 50 micrometer, and this is not possible with some other additive manufacturing technologies. So in summary, once you see direct write technology in any additive manufacturing related document, you can assume that it's about printing, producing very small products having smaller features. And our aim is actually to obtain these products without using any expensive tooling, any dye, or any lithographic mask. Since probably you're aware of that, there are different manufacturing technologies where you can produce such smaller items having small features, but they all require highly expensive tools, highly expensive machines. You need to have special dyes, or like in the MEMS industry, you need to use some special masking technologies. But in direct writing technologies, you don't need to have them. With a simple printer, you can produce such little parts with little features. And it was accelerated actually in 1990s. It's quite a new technology. We first focused on producing some electronic circuitry by depositing some conductive material on the circuits. We try to obtain such circuitry, and then people also start to use this technology to obtain mesoscale devices, not micro or macro, and some devices in between. And they try to embed some special products into these mesoscale devices like circuits, some batteries, some other actuators and sensors. And we have some companies, some technologies under direct write technology. Some of them are here for its MAPL, matrix assisted pulse laser evaporation, massive mesoscale materials deposition, or direct write thermal spraying. We will be discussing some of these in this chapter. Try to discuss the fundamentals of these several direct write technologies. And we said that in the earlier days, the main focus was on electronic components like circuits itself, the connectors, lines, and also people try to fabricate some conductors, batteries, capacitors, even some antennas were actually examined with the help of these direct write technologies. But these days, we try to use these direct write technologies for special purposes, for thermal applications, chemical applications, and even biological applications. And we have 6 types of it. we have some direct write technologies based on ink. We are using simple ink material. And then we have laser transfer. With the help of laser, we transfer some material onto the substrate or onto the layers. Or we may be using some thermal spray. With the help of spraying, materials will be deposited. Or we may use some beam deposition, liquid phase direct deposition, and lastly, we can make use of an beam tracing method to produce such smaller parts having very little features. So let's discuss the first type. It is ink-based direct write technology, and we have many variations. There are differences in terms of the technology also. It's one of the least expensive type of direct write technology, a very simple one. We make use of different types of liquid inks. I'm not obviously an expert on inks, but there are many of them like colloidal inks, nanoparticle, polyelectrolyte, depending again on specific application. Researchers select the right type of ink and try to produce such difficult parts. Since ink is in liquid form, obviously we need to have some solidification after this ink is deposited on the substrate or on the previous layer. We can have it, we can do the solidification by simple evaporation, or we may have some chemicals inside. We may do some solvent-driven reactions, start such reactions, or with thermal energy, we can do solidification. And the inks can be actually extruded through a nozzle with a continuous approach or by using drops. This is the main, let's say, classification in terms of ink-based direct write technology. And with the help of them, we can produce some difficult and little features. And in the electronic industry, the thing is that if you are using ink-based direct write technology, your extruded material should be, the size of it should be as constant as possible, and you may sometimes need to control the cross-section of it. Since if it's an electronic board, then you may have some thin regions or thick regions. Once you come up with the thin region, then you should decrease the cross-section and do your deposition. And especially this method is used for viscoelastic materials. In other cases, in other approaches, you cannot easily extrude them. Here you see some examples, fundamental sketches for ink-based direct write technologies. Obviously, the first one is an continuous dispensing, and the other one is droplet dispensing. You can see droplets, and after they are deposited on the layer, on the substrate, they are joined, as you see, but the first one is easier to obtain such continuous shapes. And for the first one, we can have nozzles, which are responsible for depositing this continuous material, or we may have like quill type of hats. They are a bit special, similar to the quill pens. You put your hat actually into a tank of material and then remove and use it on the table. And for the drops, we can use similar technologies as we discussed in material or binder jetting additive manufacturing systems, or you may generate these drops by using aerosol, some kind of sprays. Here you see the first type of continuous dispensing, the nozzle dispensing. A very simple one. We have a nozzle, material is in this chamber. It is deposited with the help of some pressure upside here. And as you see, we have a continuous deposition of material. So we can simply use pump or shunt systems. And the things are not complicated. With simple 3-axis control, you can obtain such porous structures. And we can mostly use this one for biological applications. And in terms of the nozzles, we may have various designs. The nozzle design may affect the size of your little features, and also it will affect the type of inks you can use in your application. And then we might have some difference in terms of motion control system. If you have highly accurate motion control, then that means your resolution will be decreased and your accuracy will be improved. And the pump design is also important in this nozzle dispensing systems. It actually affects your repeatability and the quality of the deposited material. And another important issue with the pumps is that you should be able to start at the desired time your deposition and stop anytime you want. This is a kind of a must for the pump. Otherwise, you'll not be able to obtain the parts, the products in 3D. Here's an example which uses nozzle dispensing approach. You see, this is the travel, this is the building volume, we can say. And if we compare these resolutions, it's quite low compared to conventional, let's say, fused filament fabrication system. Since this approach is quite similar to fused filament fabrication, it kind of has a nozzle and we are depositing material. But this time, the resolution is 500 nanometers, which is not easy to obtain in desktop or even commercial fused filament systems. Again, the repeatability is very good, 1 micrometer in z-axis. It's again, as you see, the accuracy is very good, and it's mostly used for biological applications. And in order to obtain this resolution and accuracy, they have many feedback systems on each side of the machine, and they have many closed-loop systems to obtain this high accuracy and repeatability. So what type of products we can produce with nozzle direct write technologies? You can have electronic components like resistors, filters, capacitors, some even sensors, or as I mentioned, some biological scaffolds, very small ones, can be produced with the help of this nozzle direct write technologies. And what are the main property aspects of these systems? First of all, we prefer to use them to have linear lines on the plane. We want to have some scaffolds, or we want to produce usually such kind of slices, a very simple scanning pattern. Since the accuracy is quite high, you can easily control the amount of material you are depositing into this layer. And in order to produce, obviously, this type of different products, you need to use various inks in your machine. And for the other regions of the printers, we use, obviously, standard mechanical or electrical components. And if you want to increase the resulting property of your part, then it's better you do some post-processing after you have done with after you are done with the manufacturing on the machine. Any questions, guys, up to now, up to the first type of ink-based direct write technologies? So this is the second type of continuous dispensing direct write technology. It's called as quill type. As I mentioned, it's very similar to quill pens. You put your actually pen or your hat into the ink tank and then take it out and use it on your table. And it's very similar to actually dipping your hat into ink and using the principles of atomic force microscope. You can have a look at the details. I think it's better I show you this one. If you have questions, we can discuss it. By the way, let me share the screen. Okay, this video describes how atomic force microscopes are working, and this same technology is utilized in direct write systems.
AFM is an atomic force microscope. It lets you see things that are very, very small, all the way down to the nanoscale. How does an AFM work? An AFM uses a cantilever with a very sharp tip to scan over a sample surface. As the tip approaches the surface, The close-range attractive forces between the surface and the tip cause the cantilever to bend towards the surface. However, as the cantilever is brought even closer to the surface, increasingly repulsive forces cause the cantilever to bend away from the surface.
So in printing, they use such a similar approach, but the difference is that you have some material at the tip of this microscope, and it's kind of prints some material on the sample.
An AFM has a Z scanner that moves the cantilever up and down, an XY scanner that moves the sample back and forth underneath the cantilever, and a position detector that records the bending of the cantilever. The position sensor works by tracking a laser beam that is reflected off the flat top of the cantilever. Any bending in the cantilever will cause changes in the direction of the reflected beam. The position detector then tracks and records those beam changes.
So the rest is about imaging, but the fundamental, the mechanical part is actually important for us in terms of printing. Any questions, guys, about this quill type process? Okay, this is how it works actually. This is our tip of our microscope, atomic force microscope. You put it into a kind of an ink tank, and some ink will be at the tip of it. And then while you are moving, it will deposit this material and some other extra particles inside on the layer. As you see, the advantage of this process is that its line width is very little, about 14 nanometers, which is not possible to obtain with any other additive manufacturing technologies. The resolution is 5 nanometer, so you can have different features on flat surfaces. It's quite difficult to use on conformal surfaces, but you can print little products on 2D surfaces. Now let's have a look at some discrete type of ink-based direct write technologies. The first one is using inkjet printing approach. It's very similar to the conventional printing approaches, and we need to have some mechanisms inside this hat, and it will be responsible for jetting these materials, jetting these drops on the, once again, layer. And again, it's better you use flat surfaces as possible. It's quite complicated to control it on the conformal surfaces. And we can make use of low melting point polymers or some photopolymers, since they need to be in liquid state. And after they are deposited on the layer, we should somehow obtain the solidification. And it's compared to, it has high speed and low cost compared to the other direct write technologies. For instance, if you compare with the atomic force type of printing, we have a highly complicated, costly hat, but in this one, the hat is not that expensive. And the problems are that it's quite difficult to print, as I mentioned, on conformal or angled surfaces, and we cannot have larger drop sizes in this machine. And once you are actually extruding some material, obviously the building block, the main building block, is kind of an hemisphere. It's quite difficult to draw it, but it seems that this is it's an hemisphere. And if you want to have a continuous pad, obviously, you need to have a slight overlap between these fundamental blocks. And as in the case of other additive manufacturing processes, we will always have staircase effect between the layers. But if you're not happy with that, you may use some lasers, low power lasers, and try to fuse these layers so that you will remove the effect of staircase. So if you have obviously low viscosity materials, they're quite easier to use at especially room temperatures. You don't need to melt them, try to melt them. That in that way, if you are using such materials, things will be much easier. Now, if you remember, this was the second type of direct write technology, aerosol deposition. And in this one, we have a kind of a mist, aerosol mist, and in this mist, we have ink-like materials in air. They are suspended in this mist, and with the help of some speed, they are deposited again on the substrate or on the previous layers. And for that purpose, first of all, they need to kind of have an atomization process. You start with a block of material and you try to decrease the size of the particles inside this material with the help of atomization. And you can have even metal, ferrite, and some other resistor, or even biological materials can be atomized. And once they're atomized, then with the help of the deposition hat, you can take these little particles and deposit on the substrate. And the size of these actually features can be lower than 5 micrometers. And as we discussed, even you can deposit some living cells. It's a nice feature of aerosol deposition. Let's have a look at this example from ODTÜ company. Let me share the screen. Yes, this is the aerosol jet process. They have here, as you see, atomizer. They have kind of an impactor, and this is the deposition hat. So we have the ink inside here and some material to be actually atomized. They have a kind of a screw. So these particles are actually atomized, and we have all these particles inside the chamber. And then they are actually moved to the other region of the system with the help of the pressure. So since we have gas around, we are trying to remove this gas so that the intensity of these particles will be higher, and we will have a proper deposition process. Again, they are using some helping gases. So this is how they deposit the little particles onto the, let's say, flat surfaces usually. And a schematic from our textbook. The same things are happening here, so I'm not going to discuss it once again. So in aerosol deposition, you may have high standoff and large working distances. So you don't need to be closer to the surface. There might be a gap between your surface and the nozzle. So as you see, they might be away even 5 millimeters from the substrate. You can have high repeatability, and it's quite flexible than the other inkjet printing processes. You can have different materials in the chamber. They may be all atomized, and even they have different viscosities. And by modifying the nozzle, you may have different line widths and different even layer thicknesses. But the problem is that the machine, the whole machine is quite complicated. It's a bit costly than the other ink-based system. But if you have, let's say, multiple hats, you can decrease the fabrication time. But again, the cost of the system will be increased. So now let's compare some of these ink-based direct write technologies. We have the companies. This is actually nozzle, a continuous system. Again, coiled continuous system. But then we have discrete systems here. On the right-hand side of this table, we have discrete approaches, and these are continuous approaches. So what are the benefits of, for instance, nozzle dispensing systems? First of all, you can have materials having various viscosities. It's very simple. not expensive compared to some other ones, and you can easily have lattice structures. This is especially useful for scaffold manufacturing. And if you look at the quill type, what is the advantage? Since we are using atomic microscope, force microscope, we can have nanoscale products, which is not possible with other technologies. And then if you look at the inject case, we have discrete products, and you can increase the speed of your manufacturing, since you may have multiple printing heads. And on the other hand, for the aerosol spray type of ink-based direct write technologies, you can have working distances, high working distances, which is not possible in the rest 3. So this is the main advantage we can say. And if you look at the disadvantages, for instance, the nozzle type, the continuous type, you need to know actually the surface topology before you start the printing, since you need to have a constant standoff between the surface and the tip of your nozzle. Then the main disadvantage of quill type is that you can only produce very small products. So for larger ones, this is not possible to be used. And regarding inkjet printing technologies, we need to always have flat plates. For curvatures, for form surfaces, it's not possible to use. And for the aerosol technology, the last system actually we watched is quite complicated, expensive. So this is the main disadvantage of aerosol type of ink-based systems.